Hi, everybody. Last time we introduced the topic of enzyme kinetics, which is the study of measuring how fast an enzyme operates. Now we will be discussing enzyme modulation, the factors that increase or decrease the rate of an enzyme's activity. This lecture is all about activation and inhibition, so we will first be defining the various modes that enzymes are inhibited and activated, and then we're going to correlate Michaelis-Menten parameters with the various modes of enzyme modulation that we're discussing. How do those change as we inhibit or activate an enzyme? Our molecule of the moment is going to be another amino acid quiz, so if you haven't memorized them already, get those in your noggin sooner rather than later. I like to open this topic with a question. How fast is a given enzyme? How do we compare enzyme A to enzyme B? This is an important question to consider because let's pretend you're an entrepreneur and you want to make and sell biofuels. So how do you make biofuel? Well, you get a bunch of plant starch and you break it down with an enzyme called amylase, which digests it into sugars, which you can then ferment into alcohol. And that alcohol can be sold and pumped into cars and burned to make them go. So the faster you break down the starch into glucose, the faster you make money because fermenting that sugar into alcohol is your sellable product. So what does that ideal amylase enzyme look like for you? Maybe you would predict you would need an amylase that has a very high Vmax. So let's consider what that Michaelis-Menten curve would look like. The x-axis is concentration of substrate, the y-axis is velocity. And here, this is an enzyme, an amylase, let's say, with a very high Vmax. We'll call this amylase 1. So yeah, that's a very high rate, but we really only get to experience that fast reaction velocity at very, very large substrate concentrations, perhaps unfeasibly large concentrations. So in practice, your enzyme max speed may not feasibly be anywhere near that. So, okay, maybe a high Vmax isn't all that it's cracked out to be. Maybe we want an amylase with a very low Km. Well, let's draw a hypothetical Michaelis-Menten curve of such an enzyme that has a very low Km. Bam. That curve for amylase number 2 has got a low Km. We hardly need any amount of substrate to get to our max speed, but the max speed is pathetic. So what gives? Do we decide to use amylase 1 or amylase 2 in our biofuel production business? This conundrum is what I like to call the Mario Kart dilemma. And this is a Dr. S original. If you start talking about Mario Kart to your other professors, you may get a bunch of strange looks. But I think this is a good metaphor, and this is why. If you've ever played the Mario Kart video games, you have to select characters and race them along these tracks. And some characters, like Bowser, are very, very large. They've got very large cars. Bowser's mean, so he's getting a very angry face. The character Bowser can drive very quickly. He has a high top speed, but his acceleration is poor. So it takes a long time to ramp up to that point. Compare this to another Mario Kart racer character, such as Toad. Here's another high quality drawing. So does a little guy in a little car, so he accelerates very easily. But his top speed is a joke. And once he gets there, it's not that impressive. What we need is a single parameter that we can use for across-the-board comparisons to help us decide which enzyme is better than the other. And so far, Km and Vmax on their own don't seem to cut it. Let's circle back to our Michaelis-Menten derivation briefly and recall some assumptions that we made. This might help us find such a parameter. When we saturate an enzyme, we can assume that the total concentration of enzyme in that solution is equivalent to the concentration of the enzyme substrate complex, because we have loaded up every enzyme with substrate. We can also assume that the instantaneous velocity is going to be at a maximum, because we are all the way down on the right side of our x-axis. So V naught equals Vmax. It's not getting any higher. So why is that relevant? Well, remember that we can express the maximum rates with the following expression. Vmax equals K2 times the concentration of E total. K2 is special. That is the array constant for product formation only at saturated conditions. It is a zero-order rate law, and therefore its units are going to be inverse seconds, s to the power of -1. And therefore, we sometimes call K2 the turnover number, or kcat, because that tells you how many molecules that an enzyme can catalyze in a second. Hence, that's why its units are inverse seconds, or 1 over seconds. Let's now take a gander at some of the kcats of commonly studied enzymes in biology. Catalase, for example, has one of the best turnovers, or kcats, out there. Its kcat is 40 million. Catalase's job is to detoxify hydrogen peroxide, so it's able to neutralize 40 million of those molecules in every second. I'm talking about one enzyme doing that. That's pretty impressive. By comparison, the enzyme fumarase is maybe not as impressive. That enzyme you'll see soon enough. It's part of the citric acid cycle, and its job is to react with a certain substrate called fumarate, and it's able to process 800 of those every second. So you may think that kcat can be this single parameter that we use to compare across enzymes. And you would be wrong, actually. Kcat on its own is not useful for comparing enzyme efficiencies because it suffers the same problems with Km and Vmax. We are assuming that this enzyme is operating at ideal saturated conditions. If you have an enzyme with a very large kcat, it could still be inefficient if it also has a high Km. You can have them both be very large. And what this means is that, yes, it can spit out gajillions of substrates every second, but it's going to require lots of substrate to do so. It is slow to sequester substrate, but fast to react. And on the flip side, an enzyme could have a very small Km and sequester substrate efficiently, but it could be catalytically inefficient and have a very pathetic kcat. So it can bind that substrate well, but it can't react it well. So what is the solution here? How do we figure out if Bowser or Toad is a better Mario Kart character? Here is the solution to the Mario Kart dilemma. If you take an enzyme's kcat, or its K2, same thing, and you divide it by its Michaelis constant, its Km, you will get a different parameter known as the catalytic efficiency. Sometimes it is called the catalytic ratio, which is the same thing. And its units are inverse molar times inverse seconds, which means it's a second order rate constant. And this is that all-in-one value that we've been looking for to help us rank different enzymes, because that catalytic ratio is going to describe an enzyme's saturability and its turnover. Let's now re-examine that list of enzymes that I had on the previous slide from the perspective of catalytic efficiency or catalytic ratio. We began the table in both cases with catalase, and it has a very objectively impressive kcat, 40 million turnovers per enzyme per second, which is quite a lot. Its Km is 1.1 molar, which I'm telling you is a huge number. So we're going to divide the gold medal of turnovers, 40 million, into approximately 1. So our catalytic efficiency is still 4 times 10 to the 7, give or take, which is still quite efficient, I'll have you know, but we are considerably hindered by that very large Km, which is at the bottom of the fraction. Let's now compare this to fumarase. It has a really measly kcat, 800, 8 times 10 to the 2. That's 5 orders of magnitude smaller than catalase. But check out its Km, 5 times 10 to the negative 6. That is a really low, really nice Km to have. Fumarase may not react its substrate very well, but it can load up its binding pocket like a pro, compared to catalase at least. So what happens when we divide this value by this value? A smallish number divided by a minuscule number is a big number. 1.6 times 10 to the 8. Its efficiency is 1 order of magnitude about greater than catalase. If you just look at turnover, which doesn't give you the complete story, it looks like catalase blows fumarase out of the water. But in actuality, if you look at the true efficiencies, fumarase is considerably better. Catalase is still amazing, but fumarase is about 10 times more amazing than amazing. Most enzymes don't have such high kcat over km ratios. This table actually describes some of the best enzymes out there, But this is interesting, I think, because there's a pattern that scientists have observed with these catalytic efficiencies. There seems to be an upper limit. Enzyme efficiency tends to max out at around 10 to the power of 8. You can see here we've got 3 different enzymes that act on 3 different substrates with very different KMs, very different kcats, but they all work out to be roughly the same, which I've highlighted in magenta. Enzymes have a speed limit. There's this upper limit of 10 to the 8th inverse molar per second because that's essentially the rate constant of any 2 molecules colliding in water. If an enzyme is so efficient that it reacts with the substrate faster than the substrate finds the enzyme, then diffusion to the binding pocket becomes the rate limiting step, not the actual chemistry. We call this a catalytically perfect enzyme. Another word for this is diffusion limited. Which means the formation of ES is the slowest step. Another word or term is kinetic perfection, or the enzyme is kinetically perfect. It can't be made any faster. It's uncommon for the catalytic efficiency of an enzyme to be this high, but when it is this high, it's certainly attention grabbing. Not only are catalytically perfect enzymes kind of rare in biology, in real life, enzymes hardly, if ever, operate at Vmax or saturating conditions. In fact, most enzymes have evolved so that their KMs approximate the physiological concentrations of their substrates. So physiological concentration of S often, not always, sort of equals that enzyme's Km. And that's kind of nice because that's a middle of the road value which gives the enzyme room to work faster or work slower, depending upon what homeostasis requires. And biology usually likes to be conservative. It likes to conserve its resources, and we don't like to have all enzymes running at full throttle because that would be very wasteful. So I would say more often than not, we are going to probably want to inhibit an enzyme. And we inhibit an enzyme by giving it an inhibitor, a compound that's going to jam up the works. And you were likely exposed to this when you took general biology, but inhibitors, there are many types, come in different flavors. Sometimes inhibitors can be reversible. They bind, they interfere with the mechanism, and when they're no longer needed, they unbind. They get cleared. Sometimes, though, they can be irreversible. They bind and they permanently shut down that enzyme. Many enzyme inhibitors are metabolic regulators. We will talk all about this when we dive into the metabolism units, but this is essentially the basis of feedback loops. And these are good things. They make sure that, again, we're using our resources wisely. However, sometimes inhibitors are not good. They're poisons. A poison, very often, is a compound that shuts down a necessary enzyme for bodily function. Then there's also medication. A lot of medicine constitutes inhibitors that tamp down maybe a reaction that's gone out of whack, or it inhibits a key enzyme in a pathogen that's hurting us. And frankly, the line between poison and medication is very, very blurry. It's often said that the dose makes the poison. Heroin, morphine, these are useful medications for tamping down the nervous system and desensitizing and anesthetizing someone to pain. Too much, and you shut down the nervous system forever, which is called death. So if you're interested in the fields of pharmacology or drug development or healthcare, you're probably going to be very interested in how enzyme inhibitors work. I'm now going to show you how to classify and recognize different patterns of inhibition. And the first mode is called competitive inhibition. Here, the inhibitor is an unreactive lookalike. If you were to add a competitive inhibitor to a solution of enzyme and substrate, it is going to literally compete for binding at the catalytic site. Let's take a look at our kinetic model over here in this figure A. We are including a competitive inhibitor, which is signified as I, which can reversibly associate with the enzyme to form this EI, enzyme inhibitor complex, which does not react. It takes the place of the intended substrate. Adding in this inhibitor is going to increase the concentration of EI at the expense of our reacting ES, enzyme substrate complex. So how do we quote unquote fix this? Well, the best solution is to add more substrate. Think Le Chatelier's principle. If we add more substrate, it is going to outcompete our competitive inhibitor, and that's going to drive our reaction towards ES, which will eventually help us drive the reaction towards the products. So it is reversible and circumvented by increasing the substrate's concentration. Let's see how competitive inhibition affects the Michaelis-Menten parameters of an enzyme. In the curve, I'm highlighting in yellow. That is going to represent an uninhibited enzyme. Now let's add in increasing amounts of inhibitor. the curve is going to progressively dilate. And what this does is increase the Km. The Vmax doesn't change, it just takes longer to get there. So Km goes up. Vmax is constant. Now, if you think about it, that makes total sense because once the enzyme finds the substrate, it has no problems proceeding and converting it into products. The challenging part is finding the substrate when you have these inhibitor decoys swimming about. A famous example of a competitive inhibitor that most of us likely have sampled is Tamiflu, which is more formally known as oseltamivir. This drug is an inhibitor of a certain enzyme the flu needs to infect cells. That viral enzyme is called neuraminidase, by the way, and its substrate is a sugar unit that's on the outside of our cells called sialic acid. And oseltamivir is able to mimic the transition state of sialic acid once it's within neuraminidase. And therefore, this drug is going to compete for that viral enzyme and greatly harm its ability to infect us. Most drugs, by the way, are competitive inhibitors. And I want you to notice something. The Tamiflu drug molecule, it's approximating the transition state, not the substrate. Remember that enzymes are good substrate binders, but amazing transition state binders. So the very best competitive inhibitors are not substrate lookalikes, they are transition state lookalikes, often called transition state analogs. These are a powerful subset of competitive inhibitors. If you're interested in pharmaceuticals, you best be aware of that fact. The next type of inhibition is non-competitive inhibition, or what I like to call the sneaky back door. This occurs where the inhibitor I is going to bind the enzyme not at the active site, but a separate backdoor allosteric site, and that turns the enzyme off. This effectively takes the enzyme out of solution. It becomes useless temporarily, so long as the inhibitor is bound, and its binding is indeed reversible. You can see that here in this kinetic model, where non-competitive inhibitor I can reversibly associate with the enzyme and form an EI or an ESI that cannot react. So how do we fix this? You may think, well, what happens if we increase a concentration of substrate, like we did with competitive inhibition? But if we look at this kinetic diagram, inhibitor binding proceeds just okay with or without the substrate attached because we're going after a different site. So that doesn't seem to make all that much of a difference.
However, what if we increase the concentration of the enzyme itself? If we do that, well, the non-competitive inhibitor can only be in so many back doors at a time. So the solution is to increase the concentration of enzyme. How does non-competitive inhibition affect the Michaelis-Menten parameters? I'm going to highlight the uninhibited curve over here and the inhibited curve in purple. The Km in both cases is the same. What we changed though is Vmax. Vmax has dropped quite dramatically from up here down to there. So in the case of non-competitive inhibition, it is the Vmax that suffers. And this makes sense because if we look at this diagram once again, the inhibitor does not impact substrate binding, so it's not going to impact Km. But once it's bound, the enzyme can't react at all. And therefore, the rate, the Vmax, is what ultimately gets affected. The best examples of a non-competitive inhibitor, in my opinion, are heavy metal ions, things like lead, mercury, cadmium, silver, etc. These ions all have a very strong affinity for the element sulfur. And so they particularly like to mess up cysteine thiols and disulfide bridges by essentially forming a covalent bond with cysteines. And that screws up a bunch of different kinds of protein structures, including enzymes, which just wreaks havoc all throughout the body. Some historians suspect that it was the lead plumbing in the Roman Empire that contributed to their eventual fall. Generations of drinking lead is bound to impair cognitive development and good policy making. I will say that I don't think this is a terrific example. I don't think there are many good examples for non-competitive inhibition. You'll see why soon enough. And the reason why I say that is because heavy metals form a covalent, irreversible bond with the enzyme. And in the case of non-competitive inhibition, technically it needs to be reversible. But you'll understand that conundrum by the end of this lecture. You may not have heard of this third type of inhibition called uncompetitive inhibition. And this mode is pretty nasty. I like to call it the choking on taffy mode of inhibition. And this is how it works. We have our inhibitor I, and it's going to reversibly associate with the enzyme substrate complex, not the enzyme, not a back door, but it's going to glue together the enzyme and substrate within the active site. So this is another form of reversible inhibition. But check it out. This enzyme over here is going to bite down on our substrate, and then the inhibitor is going to come in and it's going to glue the enzyme's mouth shut around its food, around the substrate. So it's kind of like we're choking on the taffy here. The inhibitor, of course, being the taffy in this analogy. So first of all, how do we fix this? It's similar to non-competitive inhibition in the sense that the only way around this is to increase the amount of enzyme. Because once the uncompetitive inhibitor clogs up the throat of that enzyme, it can't really do anything until it unclogs. Now, what about the effects on the Michaelis-Menten parameters? This is the uninhibited curve. And both of these curves are inhibited. I'm only going to be highlighting one here because this is going to get a little busy. But again, I'll highlight uninhibited in yellow. And both of these are inhibited, but just to make it easy. There you go. So what's changing here? I think very obviously our Vmax is dropping. Vmax goes down just like in the case with non-competitive inhibition. However, that's not the only thing that's changing. This is the Km of the uninhibited curve. It looks like it's around 10 micromolar. What about the Km of the inhibited one? That's over there. That looks like it's closer to 3 micromolar. Km has also gone down. That's kind of weird. Km decreasing, isn't that considered to be a good thing usually? I mean, think about it. The catalytic efficiency of an enzyme is K2 divided by Km. If you make Km very small, that's going to make catalytic efficiency increase in theory, right? Well, we have to think about the full picture here, though. We are indeed facilitating, aiding binding of the substrate by adding in a special glue into the mouth of the enzyme, but it's not reacting once the substrate gets in there. So an uncompetitive inhibitor is particularly nasty because we are removing an enzyme and a substrate from the entire system. It's a double whammy. So don't be deceived. Km is decreasing, but it's not a good thing. Uncompetitive inhibitors are quite rare, but a really good example that I found is lithium. Lithium, you may be aware, is actually a prescribed compound for people with certain mental illnesses. And it's an uncompetitive inhibitor to a certain enzyme called IMPase or IMPASE. This is a neuronal enzyme that triggers certain signaling pathways that get dysregulated in lots of mood disorders. And the lithium ion, what it does is it displaces a magnesium cofactor within the active site. The magnesium is over there. Now there's lithium. And what that does is it creates a really, really tight bind with this inositolate substrate and the enzyme itself. So it binds the substrate and it never reacts it and it never lets go. I shouldn't say never because this is reversible, but it makes it really difficult. So yeah, this is a really great way to shut down a reaction because you're arresting one enzyme and one substrate simultaneously. The last kind of inhibition is irreversible inhibition. It's also known as suicide inhibition or mechanism-based inhibition. And we call it that because usually it entails a molecule that permanently disables the enzyme's active sites, usually by forming a covalent adduct with it. So unlike all of the types of inhibitor discussed so far, this is irreversible. As the name suggests, because it's the only kind of inhibitor that's chemically reacting with the enzyme. Again, specifically the active sites. However, similar to many other modes of inhibition discussed, this has the symptom, so to speak, of reducing Vmax. Vmax will go down because we are taking enzyme out of the equation permanently. Therefore, the only way to quote unquote fix this is by increasing the concentration of enzyme, adding more undestroyed enzyme to pick up the slack. As a quick public service announcement, I like to remind my students that not all irreversible inhibitors are evil. Irreversible inhibitors sometimes get a bad rap. There's a lot of negative language that surrounds their description. Ibuprofen, penicillin, and many other kinds of drugs are irreversible inhibitors of enzymes. There are irreversible inhibitors that are evil, though. And a great example of that is sarin and most nerve gases, frankly. How nerve gases like sarin works is they are volatile organophosphate compounds like the one shown over here. And these will react with the catalytic residues of the enzymes that they destroy. And the enzyme that nerve gas often targets is called acetylcholinesterase. I won't go too deep into the physiology of this, but basically, acetylcholinesterase is an enzyme that's found within nerve junctions, and its job is to destroy acetylcholine, which is a neurotransmitter that tells muscles to contract. If you irreversibly inhibit acetylcholinesterase, the acetylcholine neurotransmitter is going to linger and keep those nerves activated, which is going to keep those muscles contracted. And that's not good for muscles like the diaphragm, which needs to contract and relax and contract and relax in order to breathe normally. So by irreversibly inhibiting one enzyme, that can paralyze the muscles needed to breathe. Let's now shift away from enzyme inhibition and towards its opposite, enzyme activation. Sometimes enzymes are deliberately produced in an inactive state called the zymogen. Also sometimes the proenzyme. This is an inactive form of our enzyme. This is very common for the class of enzymes called proteases, which digest proteins. And think about it. When your stomach makes digestive enzymes like pepsin, you don't want that pepsin immediately active the moment it's transcribed and translated, because that pepsin would digest the proteins in the cell that made it. Instead, you want to make an inactive version of pepsin called pepsinogen, which is a zymogen, which can't digest anything. It can't do that because it contains a masking sequence, a propeptide that clogs the active site. Kind of like a kid with his fist stuck in his mouth, it can't react as long as that segment is crammed in there. Only when the pepsinogen is pumped out of the chief cell and into the acidic lumen of the stomach can we change the protonation state of that masking sequence, cause it to slide out of the active site, and expose it for other enzymes to cleave off, thus turning our inactive zymogen into the active version, free to do its job, which is digest any protein in sight. This is a great example on how propeptides allow us to have spatial enzyme control. It ensures that pepsinogen is inactive inside the chief cell, but active inside the stomach's gastric juice. Inactive here, active there. This strategy of propeptide cleavage for activating enzymes also allows us to have temporal control over an enzyme's activity. And the best example of that is prothrombin. Prothrombin is eventually responsible for initiating the clotting cascade in blood. It constantly circulates in our bloodstreams in the inactive form with its masking sequence on, its propeptide shoved down its own throat. When a blood vessel is damaged, an enzyme will cut off and activate thrombin. Once that masking sequence is cut off, now thrombin is able to turn soluble fibrinogen into insoluble fibrin, which joins up into fibers that forms this giant net, this mesh that forms and traps blood into blood clots, therefore stopping bleeding. If thrombin didn't have this propeptide in place, we'd be in a lot of trouble because either our entire bloodstream would be one giant clot, so we wouldn't be able to survive, or we'd have to wait to make thrombin and circulate it in response to trauma, which is going to take a long time and risks us bleeding out before we can patch up the clot. So instead, we compromise. We make it, we put a little extra junk on to keep it in the off state, and we turn it on easily the moment we need it, where we need it. That being said, circulating thrombin levels aren't enough alone to mount a rapid and effective clotting response. Let's use some dummy numbers to help illustrate my points. How about we assume that thrombin has a K2 of approximately 10 to the power of 3 inverse seconds, which means that it's able to activate 1,000 fibrinogens every second. That may sound impressive at first glance, but remember there are enzymes out there like Catalytic that have ridiculous turnovers. 40 million reactions every second. And protease mechanisms are really difficult. It's not feasible to really get its turnover to be
extremely high. If you don't believe me, just wait till next lecture. So are there ways of improving thrombin's activity that don't involve making its mechanism better? Well, we can increase the active concentration of thrombin, and we can do that through our second strategy of enzyme activation, which is cascade amplification. And a nice example of that are clotting factors. Clotting factors, just like prothrombin, are inactive proteases. They all have this propeptide segment crammed into their active sites, like that kid with his hand stuck in his mouth. Clotting factors can cascade upon each other to superactivate prothrombin and make it induce clotting quickly. And this is how. Let's say that we have clotting factor 7. Become activated. Let's say we remove the propeptide segment off of 1. And let's also assume that all these clotting factors also have a turnover of 10 to the 3. Having one active clotting factor 7 is going to in turn activate 1,000 clotting factor 8s. And those 1,000 clotting factor 8s, once activated, will each activate 1,000 clotting factor 9s. They will activate 1,000 clotting factor 10s. And they will activate 1,000 thrombins. And those, in turn, activate 1,000 fibrins each. So let's compare and contrast. Without cascade amplification, one instance of tissue injury can give us 1,000 activated fibrins a second. With our clotting cascade, we are able to get 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000, 1,000,000,000,000 activated fibrins every second. 1,000,000,000 fibrins in a second is a blink. Only getting 1,000, not as good. I hope you can see why it's beneficial to have so many different clotting factors circulate in this inactive state rather than just having 1 or maybe 2. If one of these clotting factors is mutated and inactive, the tiniest bruise can become lethal internal bleeding. That's what hemophilia is. It's a broken amplification cascade. Things are now going to get a little bit nuanced. I now want to introduce to you allosteric effectors. These are small molecules that can activate or inhibit an enzyme. Positive effectors, also known as activators, will bind an allosteric site in the enzyme and induce a conformational change. It's going to rearrange it to be more efficient. And a consequence of that is its Michaelis-Menten curve is going to adopt a more hyperbolic geometry. Compared to negative effectors, these also bind an allosteric site and they will induce a conformational change, but this is going to hurt the enzyme's performance and it's going to cause its curve to become sigmoidal,
Another term for this is mixed inhibition. So you might be thinking, well, isn't that the same thing as non-competitive inhibition? And not quite, it turns out. Non-competitive inhibitors only reduce Vmax, and mixed inhibitors can reduce Vmax. Often more dramatically, though, the mixed inhibitor messes up the binding site indirectly through this conformational change. So in addition to the Vmax drop, Km is going to increase. And that's never observed in non-competitive inhibition. So I'll try to show that here. This is why I kind of struggled back on the slide about non-competitive inhibition, because most things that you probably had preconceptions about that were non-competitive inhibitors are usually often mixed inhibitors. It also doesn't help that very often mixed inhibition is treated synonymously with non-competitive. This is not proper. But sometimes I myself am guilty of it. So I like to warn my students to be on guard when people just talk about non-competitive inhibitors versus mixed inhibitors. Maybe the person meant one over the other. And frankly, entities that adopt a strict non-competitive mode of inhibition are really, really rare. To provide you with an example of a mixed inhibitor, I think phosphofructokinase and ATP are excellent examples. You are going to learn all about PFK when it's glycolysis time, but this enzyme's job is to commit sugar to glycolysis by phosphorylating it with ATP. ATP in this reaction is both a substrate and an allosteric effector, specifically a negative effector. PFK's active site has a very strong affinity for ATP. We need a little bit of this molecule to get the glycolysis chain going. However, if the cell begins to accumulate ATP, that means we are making energy and not using it. And biology likes to conserve its resources. So what do? Negative feedback. Those increasing ATP levels begin to induce a bind at the much weaker allosteric site, the regulatory site. The ATP made from glycolysis begins to trickle back and starts to shut down the enzyme that commits substrate to glycolysis, PFK. We can see that in the following curve over here. PFK, uninhibited, has a hyperbolic kinetic curve. If you add, though, just a little bit of inhibitor, ATP, 0.1 millimolar, we begin to make the curve more S-like, more sigmoidal. If we have more ATP, we put the brakes on even harder, and we get a very sigmoidal curve. And you can hopefully observe from this sigmoidal dilation of the curve that the Km is what's being affected
more dramatically here. See how it's moving up? And I think that effect is definitely more pronounced than the Vmax drop, if that's even happening. So you will see soon enough that it is allosteric regulation by mixed inhibition is what truly regulates metabolism. And in addition to effectors, enzymes can also be activated or deactivated through covalent modification. And there's many ways to achieve this. You can phosphorylate an enzyme, acetylate it, adenylate it, glycosylate it, I suppose. I'm not going to get into all the different ways that can happen, but the mode that I think everyone here is most familiar with is phosphorylation. Right? We've all heard of kinases, probably, right? A kinase is an enzyme that can stick a phosphate onto a nucleophilic side chain of a protein and make it negative and acidic. This is going to ultimately change the primary sequence of that protein. And believe it or not, one negative charge can completely rearrange the structure and function of a protein. It really doesn't take that much. And it's a really common misconception that I'd like to dispel that phosphorylation activates proteins. That is not always true. Phosphorylation can activate or inhibit an enzyme or protein. We will be talking about glycogen soon, and glycogen synthase is actually inhibited by phosphorylation. And what's more, phosphorylation itself is modular. A protein can have many phosphorylation sites that are accessed in a specific order, and each of those sites may have different potencies. So check this out over here. We have abstracted the primary sequence of glycogen synthase as a line, and we have identified in that line different potential residues that could be phosphorylation sites. And in this table, I don't expect you to have this memorized, but it's just to demonstrate at how much modularity there is in covalently modifying this one protein. Protein kinase A is able to phosphorylate the sites 1A, 1B, 2, and 4. This is potentially a good example of there being phosphorylation hierarchies. It's very unlikely that all 4 of those sites have the same propensity or accessibility to be phosphorylated. Now compare this to something like glycogen synthase kinase 3, which can phosphorylate sites 3A, 3B, and 3C all over here. This is great evidence how there's varying phosphoryl potency, because it would seem that turning on just one of these sites has triple the inactivating effect of any one of those blue sites. So this is undoubtedly complicated, but it's also very exquisite. The key message here is that enzyme kinetics is tunable by design, Like the gas and brake pedals in our cars, it's not on or off. We can tap, press, or floor them when necessary. These fine adjustments lets biology conserve precious resources, adapt, and ultimately survive.